All right, let's get started for today. Many announcements today. First one is about midterm 2. Your midterm 2 has been graded. You should have received an email about it from Gradescope with a link to your graded work. Solutions are posted on Piazza. Check those out. If there's anything you think wasn't graded right, please submit a regrade request. We're happy to look at that. The regrade request window is starting tonight at midnight and runs till Sunday midnight. The overall score on midterm 2 was a little lower than we had kind of anticipated or targeted. So we gave everybody a 5-point grade boost on midterm 2. There were some questions on how does this interact with the overall grading scheme. So just to clarify how things work grading-wise in 188, on the edX page, the course policy page, there is a listing of cutoffs. If you achieve a certain cutoff, you get a certain grade, let's say A, A-, and so forth. Now, those cutoffs are set based on what we traditionally believe is the right cutoff. And those are guarantees. So if you achieve a higher score than that cutoff, you're guaranteed to get that letter grade or better. If things shake out as they usually shake out roughly, then that cutoff is exactly what we'll use. If you do better than expected, that's still the cutoff we'll use, and you'll just have a very high average GPA in this class. If things shake out lower after we graded the final exam than typically is the case, then we'll adjust the cutoffs to bring your average GPA up to 3.1, which is the departmental guideline for upper division classes. So in some sense, the class is not curved because there are fixed cutoffs, but if you happen to do more poorly than anticipated, which probably means we made the exam harder than we really meant to, then we'll curve it in the sense that your grade will go up. All right? Another announcement. Final contest. So this is optional, but we'd very much like to encourage you to participate. This should be fun. It's a short window. It's between now and next week, Tuesday. You get to play against other teams from the class. It has been released, so you can get started. The ranking system will be released sometime today, we think, very likely. Your final bots are due next week, Tuesday, but every night there will be a ranking made based on submissions by midnight that night. There will be extra credit based on those to give you an extra incentive to participate. So any given night there will be a ranking. We'll count how many staff bots you edged out. You'll get extra credit based on your best night, whichever night you edged out the most staff bots, and there will be 0.25 points per staff bot you edged out on that night. If you're ever in the top 20, that gives you 0.5 point extra credit. If you're ever in the top 10, that's 1 point extra credit. If you happen to be second or third in the final ranking, it's 1.5 points. And if you happen to be first, then it's 2 points. Note that the ranking points are not cumulative, so that you can get extra credit based on edging out staff bots. On top of that, you can get extra credit based on your ranking, but that's the only way it's additive. It's not because you're ranked once in the top 10 and again in the top 10 and again and again and again that'll all add up. You can only earn that point based on your ranking once. That being said, the earlier you participate, the less other teams will be participating, and the higher your chance to be somewhere highly ranked. The extra credit points count toward your final exam score. So the final exam will be out of 100, and so best case, you stand first place, you beat all 5 staff bots, you have 4.5 extra points in your final exam. That'll be at most 1 person, or maybe 2 people if it's a team of 2, but that's the way it'll work. Any questions about the final contest? All right, look at it. There's also a baseline agent. You could just go ahead, submit the baseline agent. If you're lucky, you might make it into the top 20 with just the baseline agent on the first ranking. So that'd be a quick thing to do, but try for something more. What's the remainder of the course schedule? So there's the final contest, which is optional, but we really love for you to participate. Keep in mind also the final count is actually a little new compared to what it's been in previous years. There are now special powers for Pac-Man and Ghosts, lasers. You can actually break through walls, all kind of things that you couldn't do before. So bear with us. If there's some behavior that doesn't seem right, just send us a note and we'll look into fixing it. We think it's mostly in good shape, but since the first time, for sure, is going to be at least one bug and probably more than one. Most likely very minor, but let us know what you find. So what's left? The final contest, which is optional. There's Project 6, Machine Learning. We want you to have time to participate in the final contest, so we've decided to drop another one of your projects. So we're now dropping your 2 lowest projects, which means unless you kind of skipped on multiple projects before, Project 6 is in some sense optional or a way to just boost your project grade. It's a machine learning project. I think it's a great project, but we also understand a lot of you have a lot of extra deadlines at the end of the semester, and maybe some other classes give you extra work towards the end. We're trying to actually give you a little less work towards the end, so hopefully that balances out. If you don't get time for Project 6 during the semester, I'd still encourage you to look at it when the semester is over. Machine learning is getting more and more important out there in industry, so it'll probably be good if at some point you take a look at it and try it out. But we'll drop 2 of your lowest projects, so within the deadline pressure for grades and so forth, you probably don't have to worry about it too much. There's a practice final due on the 9th of May. Then there's a final exam on May 13th. So that's what's left. Essentially only optional things except for the final exam, which you really should participate in. Then there are 3 lectures remaining, including today. Those will cover advanced applications. What do I mean with that? We've covered a lot of technical materials. We've seen some small examples of how they might be used somewhere, but these last 3 lectures are really dedicated to seeing bigger applications. Seeing how those bigger applications tie into the concepts we've already seen. Sometimes we won't see fully how it works, but at least you'll get the intuition of how they're related. Sometimes we'll be able to see the full detail because we've seen enough to see what's behind a big, full application. They're not exam materials in the sense that we're not going to quiz you about these applications. At the same time, seeing the materials applied in a bigger context might give you more insight about what you already have covered in early lectures, so it might still be helpful for the exam. Mostly it's meant to kind of give you a bigger picture of where this is all being used or could be used in the future. Then in the last lecture, we'll also look at final contest results, and we'll look at what you can do beyond 188 at Berkeley if you want to take more classes in AI. So we'll have a slide explaining what the options are, what are good classes to take next, and so forth. Any questions about logistics? Okay, so another thing I wanted to cover is that many of you filled out our mid-semester survey, which kind of came a little before a lot of other craziness, so we didn't have time to process all of it right at that time, but I do want to get back to it because we very much appreciate you taking the time giving us feedback. A lot of the reason why the course is the way it is because past students have given us feedback and suggestions, and we like to incorporate them as much as possible, as long as we, I guess, agree with them to some extent. General impressions of the course seem to be quite positive, which is really nice to read, both for me and for the GSIs, because we've been putting a lot of time in the course, and I can also tell you no better way to motivate the staff to put even more time into the course than seeing that the time put in actually seems to be appreciated. There are a few specific things we asked feedback about. So discussion section, overwhelmingly positive feedback. There were some opposites. For example, I liked the review at the beginning of it. There was even one that said, this section is almost entirely review and I like it. Then other ones that say, well, prefer it when discussion starts with the worksheet and then asks us if we have questions rather than starting with a recap of lecture. We can't accommodate both of those in a single section, but in some sense that's not too different from the feedback we've gotten in previous years where some students asked for section to be more of a warm-up and other students wanted section to be advanced problems, and that's resulted this semester in having discussion section that's warm-up for homework and then exam prep sessions. And so we might use this feedback in a similar way. Next semester is a little late this semester for the 1 week of discussion left, but we really appreciate this kind of feedback. So maybe next year there'll be 3 types of sections. Exam practice sessions seem to be very much appreciated. Some people are suggesting that maybe we should run them even longer to have more time, because often solving 1 question already takes the entire session, but maybe solving 2 questions on a topic is better. So we'll look at that. Some people are also saying it's great, my session has only 5 people, and it's great that GSIs know me, it's nice. Other people were saying my session has 30 or more people. I wish I could get a little more attention. So it depends a little bit on what time you're going to section. Maybe something to keep in mind in general, that even if your section is very busy, there might be another section that's not nearly as busy. So maybe a little late for this semester, but something to keep in mind for other courses. So definitely something we'll do again in future semesters. This was the first time we did these exam prep sessions. We'll keep doing that. Also, the first time we did the webcasts, we did a survey on how many people look at the webcast, come to section, and so forth. Clearly, there's a lot of value in these webcasts, a lot of people taking advantage of them. So definitely something we'll keep doing. There was some great feedback on Project 4, which was a new project. Overwhelmingly positive, which was nice to read, because the 3 GSIs who put a lot of time into that, Rohin, Zoe, and Shubham, very happy to see that it actually paid off. Should say Dan Klein also participated, was essentially Dan Klein, me, and the 3 GSIs who designed Project 4. Dan, because he might be teaching 188 again in the future, and he wanted to be in the loop on what the new projects are. So thanks for all that feedback. There were a couple of constructive suggestions that we really want to incorporate for next semester, and thank you for that. I would say the main suggestion we really want to incorporate is that there was a little bit of too loose a connection maybe between the earlier part of Project 4 and then the later part, which was tying it into the Pac-Man game. So we're going to look into how tying that in more closely. Then some kind of sampling of other feedback. There were lots of positives, including about some really awesome shout-outs for many of the GSIs. One thing I want to bring up in this context is that next week, HKN will do their survey in the last lecture of the semester. These kind of shout-outs that some of you wrote for the GSIs, if you write them again in those surveys, that will actually be visible to the department and to the university that these GSIs are doing a great job. So keep that in mind. It'll be doubly appreciated, because there are things like every year there are calls for nominating GSIs for Best GSI Awards and so forth. And the easiest way for GSIs to win those awards is based on the HKN feedback survey. So if you think some GSI is really deserving of something, make sure you write something about that GSI. Even if it was not your discussion section GSI, maybe it's a GSI that always helped you on Piazza or something, feel free to grab a sheet for that GSI and write something about that. Edited lecture videos interleaved with quizzes were apparently quite popular, so we made more of them. There are about 2 or 3 still forthcoming. It takes a bit of time to put them together, but most of the ones that didn't exist before exist now. There was a suggestion about the CSP programming project. I think that's a great suggestion, and we've been thinking about it, especially since if you did Project 4, actually, you could envision that Project 4 is a probabilistic version of solving a CSP, constraints between how powers can pop up. And so there's something interesting there that could be done, bringing CSPs and base nets together in one project, something we've been thinking about but haven't had the time yet. Also a suggestion to have more open-ended aspects to the programming projects. Clearly there are the contests and the final contest where you can do something very open-ended. In general, I would say the philosophy of 188 is that we are not trying to give you open-ended projects. So it's unlikely we'd give you fully open-ended projects. We're really looking at reinforcing the concepts covered in lecture and in homework and so forth. That being said, something we are interested in and are starting to look at is having open-ended extra credit parts. So you can imagine things like you've implemented search, you now have a search algorithm, open-ended extra credit to maybe implement something well beyond what was covered in lecture and write a little report on that so we know what you did, or something where you implement not a new algorithm, but implement a search formulation, and now your search algorithm becomes applicable to a new problem beyond the problems that we fed you in the project. So those are things we're thinking of. If you have other suggestions and thoughts, feel free to email us. We're always curious to get ideas on new projects, so definitely let us know. Some issues with the grade presentation in edX. So at some point about a week or two ago, edX started crashing when computing grades. Now don't worry, your grades are in there, it's just not presenting them. What we will be doing, either way, whether the edX grades show to you again or not, over the next few days we'll generate a grade report. What does that mean? We'll generate a PDF file for each one of you, which will list your scores and everything in edX, your scores on every midterm. It'll also explain to you what's happening in terms of this is the homework that our computer program found is your lowest scoring homework, so this is the one being dropped. This is now the score based on the 8 out of 9 homeworks that we're using, and that all will be very explicit. So you'll see exactly how we're computing your grade. We'll do this well before the final exam, so you can see also how much you need to score in the final exam to be guaranteed a certain grade. Also, you can give us feedback if something was extracted wrong. Hopefully it wouldn't happen, but if it were to happen, you can tell us and say, oh, well, my grade report seems off for this and this reason, and we'll look into it. But we do want it to be super transparent to you how your grade is computed, and we will generate those reports. We'll post them on Gradescope, and so you'll have a new assignment in Gradescope where we uploaded everything for you, and that assignment will have no points out of it, but it'll just be a report of everything you've done so far. And then we'll generate a new one after the final exam that tallies up everything, including the final exam. You'll be able to see that a day or two before we finalize letter grades. So again, a chance to check that everything is right at that time before we actually submit your letter grades. So your grades will be very transparent, probably just not through edX. Any questions about logistics and the remainder of the course schedule? Okay, here's a little statistic that I wanted to share with you. We were thinking, well, she would change lecture format, because I mean, there's a lot of talk about these things like flipping lecture, which means you essentially don't lecture, you just have a recording from the past or something, or a new recording, and then instead hold extra office hours or solve problems with students. It seems that the students, at least the ones taking the survey, are overwhelmingly in favor of keeping the current format, which has live lecture and recorded lectures. The alternatives were a mandatory live lecture rather than optional like it is now, with some excused absences, which 9% of the people were in favor of. You can imagine that if you worry that you wouldn't force yourself to go to lecture, but you wish you would, that this could be useful, but not too many people in favor of that. Optional lecture videos, but no live lecture, and instead more office hours, more problem-solving sessions with the instructor then, because the instructor would not be lecturing. 15% of the students were in favor of that. About as many students were in favor of the same thing, where now it's required to watch the lecture videos. That somehow would be tracked, I guess. Not sure if we could actually do that, but it's something we gave as an option. And nobody picked anything else. You could suggest another format that maybe you thought was the right format, but nobody picked that. So it seems like next year we'll go with the same lecture format as we have this year. All right, so today we'll start looking at applications. First set of applications we'll look at are natural language processing, NLP, games, and maybe today we'll look at robotic cars. Maybe that'll be for next lecture. For sure, we'll cover robotic cars. Okay. So far, we've seen foundational methods. We've seen search, like, for example, finding a path in a maze. We've looked at adversarial cases where Pac-Man is playing against a ghost. We've looked at reinforcement learning, where you learn to act in an environment that you don't know ahead of time even how that environment works. And we've looked at tracking and estimation, where in this case, Pac-Man was trying to locate ghosts. Now we'll look at more advanced versions of those same applications. And one of the hopes is that you would see that even though these applications are more real world, that there is a close connection with the kind of more instructional examples that we've covered so far. So the advanced application that's a very clear match for search is parsing sentences, so analyzing language. Clear, more advanced application for games is a more advanced game, Starcraft. Then for reinforcement learning, Robotics has actually seen a lot of success thanks to reinforcement learning, so we'll look at some of that. And then for tracking, actually really important in robotics too, and the self-driving cars actually very heavily rely on tracking and estimation, and so we'll look at that actually today or next lecture. Let's start with natural language processing. Okay, so what is natural language processing? So let's look at a cartoon example here. What we say to dogs, okay, Ginger, I've had it. You stay out of the garbage. Understand, Ginger? Stay out of the garbage or else. What Ginger hears, blah, blah, Ginger, blah, 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 Ginger, blah, 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 blah. So what's going on here, if we think about the problem, we wish this dog was running some advanced NLP engine, but in practice, this dog just runs something called grep for its own name, right? Now, the AI for natural language processing by now is maybe a little closer to the left than to the right, but maybe not that much closer yet than we'd like. So the fundamental goal in NLP is to analyze and process human language. This could be considered in a very broad scope, should be robust, should be accurate. Systems that we might want to build, the ambitious ones are things like speech recognition, machine translation, information extraction, dialogue interfaces, question answering. More modest ones that actually work quite well at this point are things like spelling correction. In fact, it's kind of what makes it possible to type quickly on your phone, especially if you have pretty thick fingers, text categorization, and so forth. Okay, so what are some of the challenges? Why is it hard to do natural language processing automatically? Well, one of the big problems is that there are often ambiguities. So let's look at some headlines with ambiguities. Here's the first one. Enraged cow injures farmer with axe. Okay. What's going on here? Well, there's an ambiguity here between a meaningful interpretation and another interpretation of this sentence that, yes, linguistically makes sense. Is probably not what happened, what's shown over here, but it still linguistically makes sense. And so, in fact, it kind of triggers some kind of humorous note in our brains because we think, oh, well, there's this right interpretation, there's this other one, and now we're not sure what to do. Our brain trips up, and we might start laughing. Here's another one. Hospitals are sued by 7-foot doctors. Another one. Ban on nude dancing on governor's desk. Not sure which one was the real case here. Iraqi head seeks arms. Local high school dropouts cut in half. I hope it's one interpretation over the other. Juvenile court to try shooting defendant. Stolen painting found by tree. Kids make nutritious snacks. Okay, so why are those funny? Because there are two interpretations. One is meaningful, the other one is actually equally meaningful in some sense, but we know that in reality it really should not be the interpretation. So let's look at it from a mathematical point of view, what we are doing here when we're looking at these sentences. So let's say the sentence is Hershey bars protest. So you can think of this like there's some kind of protest going on at Hershey, and Hershey as a company bars this protest, send people home. So that would look like this, where your sentence consists of a noun phrase, which is Hershey, and then a verb phrase, which is bars protest, which again can be broken down then into a verb and noun phrase. Okay? So this is the kind of thing you might have done in elementary school. Get sentences, you parse them this way by hand. So this interpretation essentially says protesters have to go away. There's an alternate interpretation where you parse it this way, where you take the first two words, make that a noun phrase, Hershey bars. We all know Hershey bars is something that could be a noun phrase, and then that is doing the protesting, so that will look like this. From a pure linguistic point of view, both of them, if you just look at the grammar, both of them are valid parsings. And so the question becomes, how do you deal with that? If there is more than one possible interpretation, what are you going to pick as your proposed interpretation? So natural language grammars are very ambiguous. So what's often done, rather than having rules about that a sentence can consist of, let's say, a noun phrase and a verb phrase and so forth, we associate probabilities with each possible expansion. So we say the probability of a sentence becoming a noun phrase followed by a verb phrase is this much. And you might get this from counts. You might have a corpus of language where there are 392 sentences and 320 of them started in their parsing by noun phrase, verb phrase, and the other 72 had some other split of sentence into the next layer interpretation. You can do this for all phrases that you might have in your grammar. Okay? So the probability of a particular parse now becomes the product of the application of each of the rules. So you'd look at, well, first rule applied at the first split has some probability, then there's a next rule applied at the next split, that has a probability. The joint probability of all these splits is the product of the individual probabilities. In terms of algorithms, how do we find these parses? This is actually a search problem, right? So the way to think of this is that you currently have a partial parse tree. Initially, it just consists of S, the root node of that parse tree. But also in parallel, you have a search tree that you're building up. It's a separate tree where you're considering different parsings. And so your successor function for the search would be, for any leaf node of the current parse tree, look at what expansions exist, and any of those expansions would make for a successor. Any of these expansions would have a cost associated with them. We want to minimize cost, we want to maximize probability. The natural thing to do here would be to have a cost for an expansion that's equal to minus the log of the probability of the expansion. And so now something that's extremely unlikely, which have a low probability, will have a minus log probability that's a very high number and will have a high cost. And something that's very likely, super likely, let's say something's guaranteed probability of 1, the log will be 0 and the cost will be 0 to use that rule. Of course, this will be a very large state space and search space, so it'll take a while to find a solution with naive algorithms. A lot of work is done into how to find good heuristics for A* to effectively parse even very long sentences. So here's a long sentence. Hurricane Emily howled toward Mexico's Caribbean coast on Sunday, packing 135-mile-per-hour winds and torrential rain and causing panic in Cancun, where frightened tourists squeezed into musty shelters. There's a parse for this. If you wanted to kind of see what the state-of-the-art can do, here's the Berkeley parser. I copied and pasted that sentence into here. If I'm still online, when I click parse, it'll parse this. So it's actually live parsing. Here it is. Here's the parse. So it just found how to break up this particular sentence into its entire parse tree. This is the Berkeley parser. I believe it's available also in terms of source code, not just through the web API. And so if you ever wanted to parse something, this might be a good starting point. Of course, you want to build your own parser. What you would do is you would take a corpus, see how well this does on the metrics, and then you'd say, well, I think I can build a better one. You build your better one. You compare the statistics of your parser against this parser. If you do better, you write a paper how you're beating the best parser today. But this is pretty representative of what's possible now. This is a very long sentence. It's able to search pretty quickly to find the right parse, or the most likely parse is what I should say, because there could be multiple possible parses. This is the most likely parse based on the statistics that were collected to determine the probabilities in each expansion for this grammar. All right. Let's take a look at the next NLP system, which is Dialog Systems. So it actually was a dialogue system back in 1964. Computers were not all that powerful at the time, less powerful than your cell phone now, probably less powerful than the computer in your car, or even than an advanced microwave or something like that. Nevertheless, people were interested to say, well, if a computer can do numerical computation, it should be able to also kind of do something with language. People built a lot of chatbots at the time. The most popular one or most well-known one is Eliza. Eliza was essentially a psychotherapist. So you could chat with Eliza and get therapy that way instead of, I guess, going to a real therapist. The reason that works so well is that there was some kind of style of therapy, Rogerian therapy at the time, that people believed in heavily, where the therapist kind of always asks you to tell you more about what you just said, essentially, something like that. You'd say something and say, oh, tell me a little more about, and then pick one word from the sentence you just wrote and say, tell me more about that, and so forth. So it does a trivial string match, some substitution, and has a fixed kind of set of sentences like, I remember this, or do you often think of this, and so forth. It can fool some people for some time. Let's see how long it can keep us entertained here. So here is a live chatbot. There's a computer behind it. Hello, my name is Eliza. How may I help you? Let's see. Hi, I am Pieter. Can you tell me a bit about 188? Don't you believe that I can tell you a bit about 188? I do. Tell me something. I'm not sure I understand you fully. Problem. How about A* search as our topic of conversation? Have you asked such questions before? Maybe. You don't seem quite certain. Okay, so there's a lot of entertainment value in this chatbot, but mostly for not the person who's interacting with it, more so for people observing it. But this is the kind of bot that people were building at the time, and for maybe an easier conversation, if you start out, oh, I was hanging out with my mom yesterday, then they might say, oh, how's your mom doing? Tell me more about your mom. Do you have any issues with your mom, and so forth, and it might actually make sense if you really need therapy. Now, since then, there have come out much better question answering systems. Anybody heard of Watson? So Watson is this computer playing the game of Jeopardy, which is a popular game on TV. And so IBM designed Watson to try to play this game as well as possible. And the way the game is played is something like there would be something on the board like a camel is a horse designed by this. And then what they're after is committee, but then there's a little twist there. And you have to say what is a committee instead of just saying committee. Right? Now, there was a guy named, I'm blanking on his name, there was a special guy, Jenkins, I believe was his name, and he would win so many Jeopardies in a row, it never happened before. He would just keep winning every single one of them. Normally it's 3 people playing against each other. He would just keep winning indefinitely, essentially, knowing literally about everything. So IBM paired off Watson against Jenkins, and then Brad, who was, I guess, the second best human at this game, and just see who would win. What does Watson do underneath? So it essentially will do something like a Google search, but it won't do a Google search because it doesn't have access to the internet. It'll have pre-downloaded the entire internet into its own memory. Then when something comes in, it'll run its own version of a Google search and everything it's stored. I mean, the reason there is that it was not allowed to communicate with anybody. So it needed to be self-contained, no communication, figure out the answer on its own based on things it's found out before. It would find matches. It might then find here something like a camel is a horse designed by a committee. It might find more matches. It might then realize that committee shows up a lot in these matches and then say, okay, I'm going to answer what is a committee. So it's designed for the game of Jeopardy specifically. It does a pretty deep analysis when it parses those sentences in detail to find matches that are most meaningful. It actually won. So it won this contest and hence is the most powerful Jeopardy player. There's a little bit of a twist there that you might want to think about, which is that Watson was squared off against 2 people. And people usually know the answer to the same questions and not the answer to other questions. So in some sense, you can think of it as those 2 people splitting points between them and Watson taking the other points. So who knows what would have happened had it just been Jenkins against Watson. Maybe the outcome would have been different. But the way they played it was Watson against 2 people, and Watson won in that format. Actually, there's been a bunch of follow-up work by IBM to try to do something similar now for the real world, where you look at healthcare problems. You might have questions about your health, symptoms you observe, you want help getting that diagnosed, and the system might be able to help you out, or might be able to help doctors out finding the information they need to find. Okay, so that's question answering. Very impressive, actually, what it could do there. Machine translation, another long-standing problem. In fact, one of the early problems that was tackled back in the 50s and 60s already in AI. So what's an example of a system that you might currently see? Google Translate, right? You go to a web page that's in a different language than your default language. You're using Chrome as a browser. There'll be a button at the top that says, do you want me to translate this page for you? And it'll translate it into your default language. Okay? This actually works reasonably well. Here's an example. This is even from a couple of years ago. It's not perfect, but it's actually meaningful English that comes out. It's reasonably closely matched to what was in French. And definitely, if you don't know any French, it's a lot more helpful than just seeing the French. What does it do? Well, it somehow looks at fragments of language and tries to find corresponding fragments from the past that might be in a corpus where there is a translation for it, and then tease out those matching fragments, recompose them into an English sentence in this case. A big problem is to decide what are good matching fragments. That's a learning problem. And then a big problem is to run the search, to wade through all the statistics you collected to find how you should best recompose this original article now in English. So what's the problem with naive dictionary lookups? Well, a lot of words have multiple translations. For example, there is several words in Chinese on the left, and then the word top appears 9 times here. So that's 9 words that can be translated into top. Different kinds of tops in some sense, because the words with it are a little different. But so it shows you that just having a dictionary and swapping in the translated word is not going to do a very good job. You need something more. So let's look at 60 years of machine translation history in 60 seconds. We started in late 40s, early 50s. It was the first non-numeral compute task. People were very excited about it because the Cold War was ramping up and a lot of smart Russians out there doing all kinds of cool work, and you wanted to keep up with what they were doing, be able to understand what they're telling each other, what they're writing, and so forth. So, very important problem. And at the time was looked at, well, Russian is really something that's written in English, but has been coded in some strange symbols that aren't exactly English, a noisy version of English. I will now proceed to decode. So this is an information theory point of view of what translation really is. There was a Berkeley machine translation grant already back then, but then in the mid-60s, a bad report came out. Alpac report deems that machine translation is bad. It's not getting us anywhere. In fact, the lead of that group reporting said, machine translation presumably means going by algorithm from machine-readable source text to useful target text. In this context, there has been no machine translation. Now, okay, you might say, well, that's cool. That means we should do more work. There was a big challenge there. But the effect this had is that the government had just spent 20 years of pouring money into machine translation and just found out that those 20 years had apparently led to still no machine translation happening, and decided that maybe that was not the way they should be spending their money. If in 20 years nothing happens, what's going to happen in the next 10 years if we keep pouring money? Probably nothing again. And so, bad time for working on machine translation. Then in the 90s, statistical approaches kind of got their way in AI and started to show a lot of promise, including in machine translation. At that point, it kind of ramped up again. And at this point, there's again a lot of activity in machine translation. A lot of it driven by the fact that there's a lot more data right now. You can crawl the web, download a lot of data that tells you something about whatever that article, whatever language that is written in, gives you statistics about that language. If there are matching corpora, you know how languages relate to each other and so forth. All right, so here's an example. Let's say you have a target language corpus as one resource. I will get to it soon. See you later. He will do it. That's English. That's what we're trying to get out. Then you have another corpus, which is important, which is sentence-aligned parallel corpus, where you have yo lo haré mañana, I will do it tomorrow, and so forth, where you have pairs of sentences together. With that kind of information, the machine translation system is expected to now provide translations for things like this. Yo lo haré pronto. What's the translation of this? Well, you could look at this and say like, oh, well, maybe this part here is appearing here, so maybe that's this, who knows? And then pronto is appearing over here, but it's also appearing over here with two different meanings. So you're gonna have to somehow pick one of those two. In this case, I picked soon. It says I will do it soon as a translation. Okay, so that's what you hope to get out in terms of behavior. Now, to learn to translate, what's tricky is that if you just have some kind of parallel corpus, it's not always perfectly aligned. You still need to figure out how things match up. For example, in this menu here for a Chinese restaurant, you might say, well, if I'm interested in soup or egg drop maybe, that's not appearing as often. We have egg drop here, egg drop here, egg drop here. So we're now wondering which of those symbols corresponds to egg drop in those corresponding lines. Well, we see two symbols that appear three times, but one of those three symbols appears pretty much all the time, so probably that one's soup, and so the other one that appears all three times next to the egg drop line is probably egg drop. So if we want egg drop, we don't want to pick this one because that's probably soup, but we do want to pick this one. Is that the right one? Honestly, I don't know, but if I had to make a guess, I would guess that this is the right one, and that's how the systems also work. And then wonton, similarly there were multiple matches, but this is the most unique match in some sense, and that's what it picks to build up its corpus of matching phrases. So then how to stitch this all together? What you have is an HMM, shown here. You have the original sentence in the foreign language. That's what F stands for here, foreign language. Those are your observations in your HMM. Then the state variables, which you don't get to observe, are the words in English, the ones you're trying to recover. What are the domains of those state variables? Well, for that you could use your matching sentence fragments, you could use your dictionary and so forth, and based on statistics you could have probabilities for each of these particular observations to happen given a particular word being the word above it. So that's where you use your match corpus. Then your target language corpus, where you only have English, let's say, you can use to build a model for how English proceeds in building sentences. Now we saw that really you want to build sentences with a syntactic structure and so forth, but often people use a simplified model because it's more efficient or easy to work with. So here's a simplified model where the next word in English only depends on the previous word and nothing else. That's the HMM model, right? And so you'd look at statistics in your corpus, see how often after a given word each other word appears, and that's what's sitting on each of these transitions here. Then you run your Viterbi algorithm, and you might get out the right sentence, which in this case might be this, or the most likely sentence based on all the data you've collected. So that's HMM-based translation. You can do something more complicated. So the easiest thing is just do a word-to-word thing. You can look at phrases, which the HMM does. You can start looking at syntax, where you actually want parse trees to match up. So words, it's just matching words. You can look at phrases that you transfer over. Syntax would mean that you actually have a parse in both languages, and you want, if there's a verb phrase in one, there to be a verb phrase in the other, and so forth, but they don't need to be exactly the same structure, because one language might favor different structures than the other language, but you'll have a model for how often certain structures match up with each other. Ideally, you would go even further up and you'd actually be able to understand the sentence based on its semantics, or even bring it all the way to an interlingua, which is some kind of super language that interprets what's there, fully understands it, and then with that understanding generates a sentence in the other language that exactly expresses what was expressed in the original language. Nobody's working at that level. The highest level people are at right now is over here. So here's an example of what you might get. You get some sentence in Arabic in this case, and then you get this out over here. And this is complicated because actually the original sentence would, for example, run right to left and so forth. The structure could be quite different, but the syntactic machine translation system is able to parse through this. This is the ISI machine translation system, so you can look that up if you want to find out more. It actually works reasonably well. Yes?
What is that tag laying in like that
Which tag?
What are those two rows in between where it says like the UFP and the WR?
I'm not 100% sure what those mean. I know that some of these systems will essentially start from some original words, then re-represent them with some embedding. That is essentially representing words in a different space rather than the original word space, and use that to then do the translation. So you could imagine that, I don't know if that's what's going on here, but that's part of what's happening in a lot of current systems, where you would, instead of looking at a word as just, if you want to represent a word, you could say, well, the feature for a word is essentially a vector with all zeros, except for the one spot that indicates here that it's the 20th word in my dictionary, right? That would be a naive representation of words, all indicators for what you're looking at. A more advanced representation would actually look at a corpus in that language, would then collect statistics on, for any word, what are the statistics over neighboring words? That would be a long vector of statistics, like which words are how close at any given time. That'd be a very high dimensional representation of that particular word, which would be difficult to work with. But then you do a pre-processing and compute a low dimensional embedding of those original high dimensional statistics. And now you, for example, have maybe a 100 dimensional or 200 dimensional embedding of your statistics, and you would use, that would be vectors in 200 dimensional space, and every point in that 200 dimensional space would represent a word, or you could pick a vector there and then find the closest word. Those representations have had some pretty interesting results, where you could do things like, the sentence could be, I am the Queen of England, so to say, and then you could say minus woman plus man or something, and then in that vector space, and then it would all become I am the King of England, and it would understand those concepts because that's now how things are encoded. That's a pretty recent thing, though. I actually don't think that's what this is here, but that is often now what is used as an intermediate representation. Question there.
That's actually the pronunciation in English for the Arabic.
That's the pronunciation in English. Okay, so now we can all read Arabic, at least one sentence of it. Would you read this left to right or right to left?
No, yes, the rightmost word is that word, whatever, and then, yeah, it goes left to right.
Okay, so you're saying this thing is this thing over here?
Yeah.
Cool, well, thank you for clarifying that. And what's the next thing then? You know what this is? An alternative pronunciation? It does look fairly similar. Well, this is cool. Thank you. Any other questions about NLP? Applications we covered, or any maybe other questions about NLP? We'll see a lot more of this in the last lecture, but if you want to learn more about natural language processing, a heads up that the class that covers a lot of NLP is CS288. So you might think 288 is like the next 188, but it's actually not the way things are numbered at Berkeley. 288 is natural language processing, which is a thing you would take after 188, but it's not necessarily the next class you'd be taking. But this is the Berkeley NLP class. All right, let's take a break here then. And after the break, let's look at Starcraft. All right, let's restart. Starcraft. Anybody here has played Starcraft? Quite a few people? All right. So I will admit you're guaranteed to know more about this next few slides than I do. So feel free to speak up if you have something you want to add to what I'm saying here. So what is Starcraft? It's a strategy game, real-time strategy game where you essentially do a lot of things. You manage your economy, you might build a tech tree, you might produce units, and then might use those to attack your opponent and rule the Starcraft world. Why is this hard for a computer to do? Well, there's a lot of aspects to this game. So there's things I just described, so what does that entail? It's adversarial, you have an opponent. There's a long horizon. It's not enough to just think a few steps ahead. Remember we did minimax search, alpha beta search. You get to take an action effectively on every frame in the game. I mean, a person might not be fast enough necessarily to take an action on every frame, but a computer could. So you can take a lot of actions, and there's a lot of frames per second. So it's something that would take a very deep search to get all the way till the end of the game. There's no way anything right now can search that deep. It's partially observable in that you don't know exactly what your opponent is up to, so you have to somehow go find out what they're doing. You have to think about that. It's real time, so you can't just do a long search and then take an action and then do another long search, take an action. You'll run out of time. They'll already have long killed you before you took your 5 actions. There's a huge branching factor. There's a lot of choices of actions for you. It's a concurrent game, meaning that it's not that you take a turn, then the other person takes a turn. You're all taking turns at the same time. And there are a lot of resources that you could be relying on, which essentially make the game really, really complex in terms of how it could play out. So no single algorithm like, oh, let's just run minimax. We've seen, I mean, in principle, minimax could solve this if you're willing to wait essentially more than a lifetime for it to, and even longer than that probably, to tell you what to do. In practice, you need something that's much faster and that accounts for all of those things. So a few years ago, there was actually competition. I mean, there was lots of competitions where humans play against each other, but there was a competition for AIs to play Starcraft against each other. So there was some kind of API opened up to interface with it. This was in 2010. There were 28 teams from many different countries, certainly quite a few from Korea, were universities, research labs, and so forth. One of the entrants was actually from Berkeley. So what does this mean? You had 2 computers now playing each other in some tournament style. There would be a ranking at the end and see whoever has the best AI to play Starcraft. Okay. So what does it look like? Essentially have some kind of, on each frame, you get to decide on actions, and that just keeps repeating until the game is over. And your AI has to, in there, make decisions. The Berkeley entry was the Berkeley Overmind. What was in there? A lot of things. It was using search from our early lectures for path planning. It was using CSP solving to decide on base layouts. It was using minimax to do targeting of other troops. It was using learning for microcontrol, so it would learn to navigate in certain environments. It used inference to track other people's units, the opponent's units. Use scheduling, which is planning, which you can either do through CSPs, solving CSPs, or solving a search problem to do resource allocation. and it would do hierarchical control. Something we haven't really covered, but the idea in hierarchical control is that if you want to look far ahead and there are too many actions that your search tree is just exploding, you can't look that far ahead by looking at everything in detail, you'd have an additional representation of your problem that's much more abstract, where an action might take you much further into time. There won't be all the detail associated with this representation, but it allows you to plan further ahead. You'd first plan in there, see what plan you come up with, and then start refining a plan you made there by doing a more detailed search with the lower level actions. So let's look at some of those. So here's search for pathing. So you might have to find your way to the target that your hierarchical planner said would be a good target to go to. So see what happens here. Can you hear this at all? Okay. Wait, but it wasn't showing anything. We're only seeing things. We're only hearing things, not watching anything. That's not good. Okay. Let's actually watch this. So first one is the drone. So hopefully this will show. Oh no, this was encoded in a format that's not supported. Okay, let's do the following. Let's cover cars for the remainder of this lecture, and let's move the Starcraft explanations and videos to next lecture, and I'll bring a different laptop or re-encode the videos such that they are visible and we're not just listening to things. Okay, so autonomous driving. Starcraft next time. It's not lost, it's going to happen next time. Autonomous driving. So, what's the challenge here? You want to get a car to drive itself. What we're going to start here in our explanations is in 2005. So in 2005, DARPA essentially put forward a challenge. They said, let's see if, this is about 10 years ago, right? Can cars drive themselves across the desert without any human input? You just give it a destination. It might have a map ahead of time, but it would need to understand how to stay on the desert road to get to the destination. Okay? Well, it's 160 miles. Off-road, well, off-road, it is kind of a road, but it's not a regular road with markings. There are some hazards there in that there are cliffs, there are rocks, and so forth. There's no driver, no dynamic passing. So this was a time trial. You could participate, see how long it took. If you win, $1 or $2 million for winning the race. Okay? So a lot of teams lined up at this race. Here is actually what turned out to be the winning entry, Sebastian Thrun's group at Stanford, Stanley. But let's take a look at the overall contest here. So to give you a little bit of context, there was another one of those about a year before this, and the furthest anybody got was tens of miles, and that was it. So nobody made it till the end of the race. It was supposed to be a race, nobody made it to the end, so nobody won the prize. Then they instantiated the contest again, and now we're going to look at the second incarnation of the contest. Okay, this is.
As dawn breaks over the desert, robots prepare to boldly go where no
Can you hear this?
robot has ever gone before.
And we have movement from Stanley, ladies and gentlemen, the start of the DARPA Grand Challenge.
After months of tireless effort, there's a lot at stake.
And now Sandstorm.
A vision they all share will now be put to the test.
Launching of the sixth block here. And are we there yet?
Each one leaves the chute with confidence, a far cry from the first grand challenge when many faltered within sight of the start, and no robot went beyond 7 miles. During the first 8 miles of the race, Highlander gains 2 minutes on Stanley.
Oh no.
Behind Stanley, Sandstorm is closing the gap and may pass the Stanford robot. At mile 26, Team Dad's laser comes unbolted from the roof. Behind it, Stanley is rapidly approaching. But Highlander recovers on the flats, and for many miles they continue neck and neck.
So you always see 2 vehicles behind each other. That second one is a follow vehicle. You have an emergency stop button in that second vehicle. Once you press that, your car's done. So you don't want to press that if you still want to keep competing.
5 hours after leaving the starting line, Stanley now leads the pack, and just 5 robots remain on the course. To finish, they must wind through a treacherous mountain pass and stand. After driving 6 hours and 53 minutes at an average speed of 19 miles an hour, Stanley is about to become the first vehicle in history to drive 132 miles by itself.
All right, so they made it. 3 other teams made it too. So a total of 4 teams made it to the finish line. They made it the fastest, so they won the contest. Here is some other footage of just to kind of illustrate that this was a highly non-trivial task, definitely at the time. Of course, now it's better understood, and in big part thanks to the work done then. But things can very easily go wrong if you try to build an autonomous car, or the Berkeley entry, autonomous motorcycle. Self-riding motorcycle. All right, you get the idea. So it's actually highly non-trivial, and there were many groups who participated. 4 made it to the finish line. Actually, a pretty close call. The timing wasn't substantially different between the first and the second team, but as the way it goes, if you're first, you take all the glory. So this is the car of the winning team, Stanley. So this was a Stanford team led by Sebastian Thrun. So what was on this car? An inertial measurements unit, which measures your acceleration, your angular rates, and measures magnetic field, so you know which way you're headed. 6 computers, a GPS compass, a GPS, an emergency stop, 5 lasers on the roof, also a camera, a radar, a control screen to see what's going on, and a steering motor. So one of the things you of course think, well, steering, how do you do that? Steering, that's really a search problem, right? You search over a sequence of actions that you might execute. You build a simulator for your car. You might have a reference trajectory you're trying to follow, and now you simulate different possible sequences of actions, see which sequence of actions leads to the closest following of that trajectory, and that's a way to follow trajectories. It's actually called model predictive control if you do that, and that's what still now is the state of the art to control cars onto certain trajectories. Of course, a big part of what's challenging here is to understand where the road is and what's around you, so you can actually choose your reference trajectory. So if you have an empty road, your laser reading, so how does a laser work? You send out laser beams, you see how long it takes for them to get back to you, then you multiply that time with the speed of light, and now you know how far away whatever it was that laser beam reflected on is from you. So you have a really precise clock, otherwise this doesn't work, of course, but those clocks exist, and you can do this about 2 centimeter accurate. So you can send out a beam and 2 centimeter accurate know how far away the thing is that reflected it. Okay? So now if your road is flat, this is what you'd get if there's an obstacle somewhere. Let's look at an obstacle scenario. Here's an obstacle. What would happen is you'd get a shorter reading, because it wouldn't go all the way to where the pavement is. It would be obstructed earlier, and now you'd know that you're encountering an obstacle. You know in which direction you encounter it, and you can map out in 3D what the environment looks like in front of you. So now one thing with these lasers is that they're notoriously noisy, that they could reflect on spurious things that are not actually obstacles. You might lose some readings and so forth, because if you, let's say, have a mirror and it's not perfectly looking at you, then the beam will hit the mirror and it'll reflect away, not come back to you, go somewhere else. So to account for the noise in there, one thing you can do is say, well, the obstacles around me aren't changing super quickly. I can essentially think of it as some kind of state of the environment. What is the environment like around me? I'm not directly going from these laser measurements to saying, oh, this is what the world is like. I'm just considering the current laser measurements as one observation, and at the next time I get another observation, and so forth. All right, so raw measurements would give you 12% false positives. Now, if you build an HMM around this, and you also use, of course, your GPS and IMU to know how much you moved, you can reduce that from 12% false positives, which is false detections of obstacles, to only 0.02% false detections of obstacles. The other thing you might want to use is a camera. You might say, well, why use a camera if you already have a laser? Well, there are a few reasons. One thing is that the laser indeed could, on a reflective surface, a very reflective surface, like a mirror or a window and so forth, it'll actually not come back at you. It'll kind of make the reflection in a very particular direction only, and you'll lose that beam. So it'll look like a dark spot. You won't know what's there. That's actually not distinguishable from just things being very far away. If you point the laser to the sky, nothing will come back. You point at a mirror at any angle except for 90 degrees, you get nothing back. So you want additional information from something else. The other thing is that these lasers can only look so far ahead. With a good laser outdoors, maybe you can look about 30, 50 meters ahead, but that's it. You can't look beyond that because you won't get anything back from beyond that. So how do you look further ahead than those 30, 50 meters? So you might want to use a camera. A camera can look very far ahead. Flip side, a camera doesn't give you 3D information. It's much harder to process the information that's in the camera view. Right? And you want to recognize things. You want to recognize road versus trees, so you don't end up doing something like this. Now, what was really interesting in the winning entry is that they built a vision system for their car that was actually trained with machine learning. It's very hard to just hard code rules about if I see this in the image and these pixels here or there, then it's road, but otherwise it's bushes and so forth. You can try something like greenish is bushes and so forth, but that's not very robust in practice. So what they did is they started with actually using their laser, And so this driving is done with the laser at a modest speed, and the laser maps out the 3D around the car very accurately. And now what it does is says, well, I've mapped out where there's road, where it's not road. Since I've mapped that out, I can actually now use this as training data to train my vision system based on camera images, and you see the result here. So you effectively get self-supervised training. You don't have to collect a lot of images and delineate where the road is. You collect the images, the car is driving through that environment, and after the fact, because you know how your car drove, you can go back to your images and automatically annotate where far away from your car the road ended up being or not ended up being. Now, as you know, machine learning, the biggest part of the game tends to be to collect enough data. That's what makes things work better. And so this was a very clever trick to get a lot of data to train their machine learning system to recognize where the road is. And so here you see the result of that in action, where it's clearly aware of red is road, green is not so sure, probably not road, and you can see how it actually figures out where the road is and how to go down this particular path. Now, after they did this, the DARPA challenge in 2005, 2 years later, there was an urban challenge where they said, we now want this to work in real cities. Okay? So maybe with people, other cars, and so forth. So it's more complicated. There's much more variability. In general, the more variation you have to deal with, the more difficult things become. All right? So here's the first thing you can look at. What you see here now is a Velodyne on top of the car. So one of the results of this 2005 challenge is that a company that makes speakers, Velodyne, decided to make a different product because they were excited about this challenge, and apparently the expertise for making speakers is quite related to expertise for making good lasers to bolt onto cars. And so they built this Velodyne laser that can spin around very quickly and gives you hundreds of megabytes of data per minute that give you the 3D information of what's around your car. In fact, a lot of the Google cars have exactly this laser still bolted on top, even now 8 years later after they released it, and all the teams in the Urban Challenge used it. And you can see how you get a nice 3D map of what's around you. Now, beyond building that map, you actually need to track what's happening around you. So just like we had tracking of ghosts, what you have here is a demo of tracking of pedestrians. So yellow is pedestrians, and they're being tracked. The car stops to let the pedestrians pass. There's tracking of static obstacles, which is red. There's tracking of the road, and so forth. So this actually worked reasonably well. By the time the Urban Challenge came around, there were 6 finalists in the Urban Challenge. Was, I believe, Carnegie Mellon, MIT, Cornell, Stanford, and I'm blanking on the other 2. And all 6 finalists did really, really well in navigating this urban environment at the time without pedestrians. What happened after that, around 2007, Sebastian Thrun, who was the lead of the Stanford team, actually also had a startup which turned into Google Street View. Then at Google, he talked with people there, and including people who are in charge, Larry Page, Sergey Brin, and convinced him that it's a good time to start working on self-driving cars at Google. So he then originated a project there, essentially hired all the prominent players from the other teams into the Google self-driving car team. Beyond that, had them start Google X. So he's done a lot of things there, very effective. And so the most advanced car now, arguably, is the Google self-driving car, which in some sense the culmination of all those teams working on these challenges and then doing a lot more work since they got to Google. And here's the kind of capability that car has. This is a video from the Google car in autonomous driving. So this is San Francisco. It's dealing with other cars. It's dealing with pedestrians crossing. It understands the stop sign. This is a toll plaza that's difficult to navigate. This is probably scary if you're sitting in the car. At night, another toll plaza / merge. So they've done hundreds of thousands of miles autonomously. They're still fine-tuning, but there are actually now driver's licenses out there. Like, for example, in Nevada, you can have a driver's license for an autonomous car. At least that possibility exists. Something came into law a few years ago. So there's a lot of progress there in terms of where we're at. Since a few years ago, a lot of other companies have jumped onto autonomous driving too. Tesla has been looking at autonomous driving. A lot of the traditional car manufacturers are looking at autonomous driving. Also, a lot of startups building specific products. For example, there's a company called Mobileye that essentially provides a smart camera that can help you detect pedestrians, other things that your car might care about that you might add on. As a manufacturer, you might say, well, we don't maybe know how to build an autonomous car, but let's partner with Mobileye, put their system into our car, and so forth. So question there?
Yeah, I was wondering, how do the cars deal with things that require like human interaction, like if they're at like a toll booth, what do they do?
Not sure. So one of the issues here is once it went into Google and into corporate research, it's less clear what exactly they're putting underneath. They're not giving away their specifics of how they're doing things. Every now and then they release a video so you can see what their capabilities are. So I don't know what they do to deal with that. My assumption is that they, some things they'll hard code. I'm sure they hard code things for stop signs, but it's like if nobody moves, maybe it's my time to move, or if somebody else moves even on my turn, let's stop anyway, even though it's my turn, and so forth. I think a lot of it is that you drive so much, and when you drive hundreds of thousands of miles, you see a lot of corner cases, and so you can inspect them by hand and see when did the human driver decide to intervene. Let's inspect those cases by hand. Let's see what happened. You might hope that they just machine learn based on the human intervention, and that's good enough. But for that, you might need a lot of special case scenarios that you encounter. Not sure what they're doing. Oh, I'm assuming they have a fast track for that. So that'd be a whole different capability. You're right. All right, that's it for today. Next 2 lectures, we'll see more advanced applications. Hey.
The Starcraft video might not have worked because it might have been an actual Starcraft replay, which requires the game to move. I'll have to see which one.
That might be true. On my Mac it worked when I was checking it out this morning, but my Mac doesn't have a screen I can write on, so that's why I then transferred onto this machine to lecture. But the next 2 lectures I don't need to write anything on screen, so I can just use my Mac and it should work. But yeah, I think for the original production of videos that might have been true, but they were screen captured from that. Do you play a lot?
Used to.
Used to? Less time now?
Yeah,